Pamela, can you hear me?
I can.
Excellent. And I can hear
Wow, you were
you.
loud. Okay,
I'm as,
finding the volume.
it's not it's not my fault. It's Google's fault, as usual.
I can still work to figure out how to turn you down.
Turn your you can't turn this down. There's no way this is getting turned down. Hey everyone, how's it going? Welcome to a live episode of Astronomy Cast. I'm Fraser Cain. That's Dr. Pamela Gay. And you have joined us to watch us record our show live in real time. How's it all going there, Pamela?
It is much better now that I have adjusted the volume and you are no longer inside my head, but merely
I'm
on the edge of it visiting.
I'm also not yelling. I can, and I might again. So we don't know. Okay, so this is a live episode of Astronomy Cast. If you have no idea what this is that you stumbled into, so I'm going to say hello to Noel Ruppenthal, Douglas Crandall, Richard Clark, Andrew Planet, Nancy Graziano, Guido Bieber, Tony Lynch, Peter Waldman, Tom Nathy, Oleg Straganoff, Albert Braun, Thomas Tranneker. My favorite people here. Ed Thompson. This is awesome. Hey, everybody. Welcome. I hope we can do this, use some service.
It's great seeing all of these people week after week after week, and we appreciate you bearing with us last week while you were on vacation and I was in the Czech Republic.
Yeah, that was a strange coincidence. But we're back and we're doing this thing that we like to call Astronomy Cast. So this is a live show. I promise you, if you ask a question, we will see it and we may or may not answer it. But you can do that by going to the Q&A app. So wherever you're watching this, you'll see the video. It says we're interacting with the audience. Click that. You'll get another version where you can watch the screen, but also have a bunch of questions you can ask. We don't have a lot of time because Pamela is in frantic preparations for the Hangout-a-thon, which is coming up just this weekend. So
yeah,
that's the thing. 36 hours of watching Pamela go crazy.
Well, you're going to step in for 6 of those hours. So 30 hours of me going crazy and 6 hours of you holding down the fort.
I've done 6 hours of live broadcast has not driven me crazy in the times I've done it in the past. So I think we'll be all right. 36 hours, that may send you to some dark Cthulian nightmare.
I've done this before. I have good help coming and good help on the internet. It's the organization that may kill me.
Right.
I am on my own organizing it this year because due to funding cuts, I've got no help.
Right.
Yeah, we really need this to be successful.
But yeah, so more details coming out. Where can people, if they want to sort of find out the details, where can they find them?
CosmoQuest.org/hangoutathon.
Perfect. And you can see the lineup as it starts to come together, the dates, the times, the places to watch, where the video is going to be embedded, all that good stuff.
All of the Hangouts are already set up. There's a few typos I need to fix, so please be forgiving. But go ahead, RSVP, and plan to spend your weekend with me.
That sounds great. With us.
With us.
Okay, cool. So yeah, so like I said, we don't have a lot of time. We may answer a couple of questions, but we'll probably just wrap things up pretty quickly. So once we've done the show. Okay, well, you tell me when you're ready and I will press record.
I am noting that there's huge chunks of ice falling out of the sky in Atlanta. Be safe in Atlanta. And I'm now ignoring Twitter and pressing record. And I'm not recording in mono because it's that kind of a Monday.
Okay, stop. Well,
okay.
Be careful, Susie.
Yeah, and Swoopy.
And Swoopy, yeah, Susie's our producer, and she's getting rice.
It's like a giant. Swoopy just posted pictures of like almost golf ball sized chunks of
hail.
Ice
wow,
from the sky.
Yeah, we have just insanely warm weather here right now. 21 degrees today, so.
Yeah, we've already had our first set of tornadoes, and I think we're due for more this week. So it keeps it interesting.
All right.
But I'm now ready to press record.
Thanks, climate change. Okay.
Yeah, seriously. Okay, pressing record.
I've also pressed record.
Recording. Hi, Preston.
Hey, Preston. Okay, here we go. Astronomy Cast, episode 374, the Stern-Gerlach Experiment. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good, although saying professor of Southern Illinois University, Edwardsville is actually tough. I struggle with it every single week. I have struggled with it for almost 400 times now, but we made it through.
It line wraps.
Exactly. It's a very long title. Okay, so we can talk about the Hangout-a-thon, but I think by the time people listen to this, it will have already happened.
It will, but it won't be too late to donate. The weekend before this goes live on the internet, we are recording 36 straight hours of video on Google Hangouts and trying to raise money to keep CosmoQuest going. Without your help, we're kind of done for. And I don't mean to sound black, but that is the actual literal truth. I'm in the process of writing a giant NASA proposal. But if we get it, we won't get it until October, and we need to keep things going until October. And we can only do that with your help. So if you missed the Hangout-a-thon and you want to see me keep doing awesome citizen science projects that allow you to contribute to publishable NASA research, go donate. CosmoQuest.org/hangout-a-thon, all one word. Every little bit helps. $10 is more than an hour of a student's time, and we need those students back.
That would be great. And let's get on with the show. And you should also just watch Pamela go from a sane person to a crazy person over the course of 36 hours.
You keep saying that, but it hasn't happened yet.
This third time's the charm.
I did confuse Prosecco and prosciutto last year, but that was a tongue twister.
Okay. Not an actual descent into madness. All right, let's get on with the show. So in the world of quantum mechanics, particles behave in discrete ways. One breakthrough experiment was the Stern-Gerlach experiment performed in 1922. They passed silver atoms through a magnetic field and watched how the spin of the atoms caused the particles to deflect in a very specific way. So quantum mechanics, it's been famously said, right? If you think you understand quantum mechanics, you don't understand quantum mechanics. So before this experiment, can you again set the scene?
Well,
I guess where were scientists at their understanding of quantum mechanics?
We'd gotten to the point of we understood that energy was quantized when it came to how electrons existed inside of atoms. So there was this notion that an electron had an allowed orbital energy, that you could have up to 2 electrons per energy state. This is the Pauli exclusion principle. We'd started to get to the idea that there was an extraordinarily dense nucleus, still didn't know what was holding it together. We had gotten to the understanding of just how empty the rest of the atom was. But we were still confused with things like magnetism. There was the understanding that a charged particle in motion interacts with magnetic fields, generates magnetic fields. And an electron in an atom is kind of a charged particle. And so there was the question of, are these magnetic states, just like the energy states, also quantized? We didn't know, and that was what led to this experiment.
Okay, so describe the setup then. How did they perform this experiment?
Well, it was 1922, and the place was Frankfurt, Germany. We had 2 scientists. There was Otto Stern and Walther Gerlach. And what I loved is where they were located at the University of Frankfurt. You didn't just have a physics department. No, that was far too mundane. They had an Institute for Theoretical Physics, which is where Stern was located, and they also had an Institute for Experimental Physics, which was where Gerlach was located. And I find deep pleasure in the fact that they sort of like isolated these two communities from one another. But Stern reached across the institutional divide and asked Gerlach, can you devise an apparatus that we can subject charged particles to, in this case, silver? And can you do this with a sufficient magnetic field that we will be able to tell are the magnetic states a continuum or discrete?
It's sort of back to that same question that we talked about a few episodes ago, right? Is it digital or is it analog, right?
Exactly.
And so, okay, so you're saying, like, can there be a discrete state? So what does that mean then? If there is a discrete state for the particle, what are the implications as opposed to it being just a continuum?
Well, in this case, if there were discrete states, when they sent a stream of silver ions through the, in this case, inhomogeneous magnetic field, the silver atoms would split, some going one direction, some going to the other direction, depending on their magnetic state. And so what you'd have is literally a splitting up based on magnetic field, one atom to the left, one atom to the right. But if instead you had a continuum of states, you'd have a smearing of the atoms instead, where they went variable amounts to the left, variable amounts to the right, and some of them just didn't really go anywhere. So these were the expected outcomes of the experiment.
Right. Okay. So I can sort of imagine that it's like if it's some you take the charge on these electrons, if it's some multiplication of the basic charge, then they're going to lock in and they're going to get that spin out. Otherwise, they're going to go the other way as you tune the magnetic field, right?
But in this case, the charge is the same. It's the magnetic state that they were thinking might vary.
Right. Okay. And but then as you said, if it's a continuum, you just get this spray depending on, each individual electron. Okay. So they ran the experiment, they had the expected outcomes, and what did they find?
Actually confusion, because as they were preparing to do this experiment, it was realized, insert expletives in German, the angular momentum of electrons just might be zero. So if this was the case, instead of expecting a dichotomy of to the left, to the right, what they actually expected was to the left, nothing to the right. So split of three different things. So there was this sudden, we've been working on designing it. Oh, let's change what our expectations are now that we understand more about the angular momentum, the orbital angular momentum of the electron. But then the results they got was actually this splitting that didn't match that expectation at all.
How did it split? What was the result? Tell me, Pamela.
Well, the result was the original sum to the left, sum to the right.
None to the middle.
Yeah, which was kind of a head scratcher.
So then, once they had sort of seen that, then they knew that it was it was magnetically quantized.
No, they initially just knew it was confused.
Okay.
So what they had was this problem where they'd initially assumed that the magnetic moment that they were dealing with would come from the orbiting electrons in the silver atom. And the reason they were using the silver atom is because you have all of these stacked energy levels, and in the final energy level, you're left with one unmatched electron. And that one unmatched electron was going to be providing the magnetic moment, the orbital magnetic moment for the atom. But then they realized you can actually do a lot of cancellation, and that orbital angular momentum goes to zero. But what they hadn't thought about is, well, what if the electron itself has something that we can't really describe except to liken it to spin? So if you think about it, the Earth has orbital angular momentum related to our passage around the sun each year. That's one set of angular momentum, and it's that kind of orbital angular momentum they were expecting to create the magnetic moment, the magnetic field that they were trying to find.
Right.
But
they were imagining the silver atom as a little solar system.
exactly.
Yeah.
And that's a bad way to look at it, but it's still the best our human brain can really do. But the other place that we have angular momentum is our Earth is kind of rotating about its pole. Our day-night cycle is another spin that creates angular momentum. And when they looked at their results, they realized, wait, what if in a classical imagining of what's happening, we consider this as rotation about a pole of the electron where you have north up and north down, creating two different kinds of, in this case, spin magnetic moments that are creating this to the left and to the right, splitting of the silver as it goes through the homogeneous magnetic field.
Whoa.
Yeah.
So I guess the question then is like, did this give them a better understanding of what to move away from that solar system idea of the atom into this more, because I mean our modern idea of the electron, we call it the electron cloud, right? That it's not these atoms or these electrons just spinning around like little planets going around a sun, that it is a region of probabilistic sense. So I mean, did this give them some of that understanding?
It didn't quite get them there yet, but what it did start to get at was the notion that the electron was a lot more complex than originally assumed. We now have a particle that we know has charge, that we know is a fundamental particle that you can't really break apart any further, but it somehow has its charge, if you look at it from a classical approximation, distributed on the surface of this point, and that's kind of confusing. It also started to help add further understanding to another phenomena. It was realized that hydrogen has this weird line that appears at what we now look at as 20 centimeter radiation in the radio. This is the hydrogen fine structure forbidden line transition, where there's actually energy tied up in whether or not what we now know, or at least now refer to as the spin of the electron and the spin of the proton, if they're aligned, that's one energy state. And if they're out of alignment, that's another energy state. And we can now see this weird line and understand it using this magnetic spin.
So you as an astronomer, you are looking for places, regions of that kind of hydrogen, right?
Exactly, and we find it. It's a very infrequent. This hyperfine structure transition is a very infrequent transition, but when we look at massive clouds of hydrogen gas that don't have that many collisions going on, it's possible for a hydrogen atom to just hang out long enough that it has a chance for this flip at, sorry, it's the 21 centimeter line, this flip at 21 centimeters. And we see it. And understanding this hyperfine structure wouldn't be possible without the Stern-Gerlach effect.
But when you see that it's like in spectroscopy, right? When you see the presence of the hydrogen at that specific wavelength in some big vast cloud of hydrogen, what does that tell you as an astronomer? What process is going on there?
What it tells us, first of all, is it's a really boring cloud of gas where very few collisions are taking place. If collisions were taking place, other forms of energy transitions would take priority, and this very rare transition would never really statistically have the chance of happening. So first of all, it tells us the gas is boring and not colliding a lot and just hanging out. The other thing it tells us is that you actually can change energy states just by changing how the magnetic fields are aligned. And this kind of makes sense if you've ever played with bar magnets. If you try and push the north end of two magnets together, that takes energy. Whereas if you try and have them anti-aligned with the north to the south and the south to the north of the two bar magnets, that will readily snap into place. So it's that difference in the required energy, the difference in the energy with the two particles, depending on how they're aligned, that causes a photon to be released with this very particular 21 centimeter radiation.
But I mean, it's not star forming regions. It's not.
No, nothing
cold,
that exciting.
But it's like cold. But isn't it like cold hydrogen gas left over from the Big Bang?
Right.
That hasn't gone.
It can be reprocessed.
Right.
It can be hydrogen. It literally simply means this is cold gas that isn't undergoing a lot of collisions.
Right. And is not in the process of forming new stars or whatever, but could be clouds for future use. Okay, so let's go back to the experiment. So they performed their experiment. They got their result, and how was that accepted by the scientific community, and what were the implications?
Well, initially it led to a whole lot of head scratching because, as I said, there were these two theories on what should come out. One was initially the split two ways, then it became split three ways, but then they actually saw it split two ways. And so the motivation for this theory was, well, it was a man named Summerfield who came up with the initial theory that led to this experiment, the theory that it would get split the three different directions. But like I said, this was one of those moments of experiment to not do what it was supposed to do. And even with the original split a lot to the left, split a lot to the right, nothing in the center, that splitting was based on the orbital angular momentum, which was a very different value from the spin angular momentum. So what they were seeing was still less of an effect than what was expected.
It's such a strange thing to think about when you think about actual atoms and each individual atoms having angular momentum.
Yes.
Right? Like you don't and the electrons themselves as part of the atom and that having this, containing some of the angular momentum. It's not, I don't know, it just seems really strange that you could break down the universe into these little pieces, and then you realize that the angular momentum of entire structures is made up. You just add them all up, right?
And what gets me about this experiment as well is they did this in 1922. And this was not an entirely safe experiment to be doing. Silver atoms aren't something that are just regularly hanging around all by their lonesome. They had to superheat the silver to get it in a pretty much gaseous form going through their inhomogeneous magnetic field. And the reason they were using silver was, like I said, because it has this final electron by its lonesome in an outermost orbital. They also chose it because it was readily detectable in their photographic plates. Let's face it, silver's kind of easy to spot when you fling it onto a photographic film.
Should we be breathing superheated silver gas?
No, not really. No, it's
Okay.
just not the healthiest thing for you. So here they were in 1922. We didn't have amazing electromagnets like we have today. We were just starting to figure things out like that. We didn't have the machine shops we have today. We didn't have the vacuum hoods, all of these things that would have made this a relatively straightforward, relatively safe experiment. Instead, we have a theoretician saying, I need this level of magnetic field to detect this effect. We have an experimentalist saying, okay, I've got it. And than working together with silver gas.
One of the things sort of talking quite a bit about with this experiment is just this concept of spin. And I think this comes up quite a lot through quantum mechanics and through physics, this idea that things on a particle like a proton, in an atom are spinning. So when we talk about spin in terms of physics, what are we talking about?
This is where we get back to your originalist statement of if you think you know quantum mechanics, you probably don't. Spin is a word that we use because it allows us to think about what's going on from a classic perspective. You can imagine the electron as a sphere with the charge on the outermost parts of the sphere, and as it rotates, just like the Earth's rotation generates a magnetic field, the electron spin would generate a magnetic field. The thing is, that's not actually what's going on, and we're not really sure what's going on because it's not like we can go in and observe the very essence of an electron. There are people that argue that this is one aspect of string theory, where when you see one spin, it's because you're looking at one end of a string that is mostly rolled up into other dimensions. And when you see the opposite spin, it's because you're seeing the other end of a string that's rolled up into other dimensions. But this whole notion that it's an electron with charge on its outside, that's just what we tell ourselves to make our brains not quite hurt as badly.
And when we say that something is spin up or spin down, right? Like, what are we talking about?
It's literally, does it go to the left as it's going through a magnetic field, or does it go to the right as it's going to a magnetic field? That's our way of, you might say one's north, the other's south, but that implies monopoles. So that's not, we can't use those words, but it's literally a way of expressing how it interacts with the magnetic field. You might think of it as North Pole is aligned upwards versus South Pole being aligned upwards.
Right. And it's like a bar magnet, right? Like it's a binary situation, right? You have a bar magnet, it's got a north south, you bring the North Pole to it, it's going to flip it around and clamp onto the south end, but it's not, and I guess as it's moving through that magnetic field, the magnetic field is then getting them to align into the right alignment to whether they're going to veer up or they're going to veer down through that magnetic field.
And where it starts to get wrong as far as your stomach is concerned, because your stomach will try to do physics and fail mightily, is the spin is actually looked at in terms of different magnetic moments where you might have its spin is +1/2 or -1/2, or its angular momentum we'll look at as being -1, 0, +1. And these are numbers that we use to represent what's going on. But it's important to understand that a lot of the rules of quantum mechanics are tools that we use to describe what we experimentally determine, but that doesn't mean they're actually describing the physical reality of what we're seeing. It's just a set of instruments, a set of math that allows us to get at predicting what will happen next. But that's all it's doing, is very successfully predicting what has happened and explaining what we've seen.
And we did a great show. Go back into the archive. We talked about entanglement, and spin is one of these characteristics that physicists use to demonstrate entanglement. And so you can sort of take this experiment to the next level, right? You can really contort it and start to get at these entangled properties of these atoms, as these electrons, as they're passing through this apparatus.
And as you try and put this together, they got lucky with their particular atom of choice. It had a orbital angular momentum of 0, and so we were dealing with the electron's intrinsic angular momentum, which is ±1/2. But not all systems are equally elegant. Other systems, you end up with additional magnetic moments that come from the orbital angular momentum being some different integer than, well, 0. And so you have to add up all of these different bits to get at the total angular momentum, which reflects on the total magnetic moment of these particles and these atoms.
Had a lot of work been done, because it feels like this was sort of one of the parts of why it's such a groundbreaking experiment, was that from the moment they started to take atoms and run them through these magnetic fields, they really started to tease out a lot of the fundamental measurements, characteristics of the atoms, and that variations, flavors of this experiment are still being run today, just in more complicated, higher energies. But still, this is the way, apart from smashing them together, this is the way that physicists are getting at the fundamental way that, the measurements, the masses, the spins, the charges, all of this stuff, they're by running them through these kinds of and entanglement, right?
And that's entirely right. When this started, we were just starting to understand that the electric and magnetic forces were coupled. We were just starting to understand how charge generated magnetic fields. We were still only a generation into this, where a lot of the discoverers in the late 1800s were still around as your senior emeritus faculty, and it was the new junior faculty who were playing with the new massive alternating currents that were being devised through new forms of generators. It was new, more precise machining apparatus that were allowing us to do more and more detailed experiments. And then, of course, photography. That was still in its infancy back then. But at least at this point, infancy meant 40 years in when we hit the 1920s. So everything was still new, and when you coat it with silver, shiny. And they were working hard to figure out all the new characteristics of the charge that Benjamin Franklin had started working with in the 1700s.
Yeah, and the calculations that Maxwell had done to really integrate magnetics and the electric field, right? So.
And we were starting to get to the day of Dirac notation to try and understand how you add together the magnetic moments. We were starting to get to the Schrödinger equation to describe the wave nature.
Dirac was the one who predicted antimatter, right?
I don't know. That's a different episode.
I just did a show on it, so yes. I forget the date, 1928? Anyway, cool. Well, that was awesome, Pamela. That was great, and we'll see you next week.
Sounds good, Fraser. I should stop my recording.
Does you want to just keep on going? Extra show. Save.
Oh, I can't believe I said 20 centimeter instead of 21 centimeter. Internet, be forgiving.
So wrong. It's okay. Preston will edit it out. He'll know that's really important. Man, what are we? 374? Wow. Okay.
We'll hit 400 by the end of the year, I think.
Yeah, we have to figure out the date that we go on hiatus. End of June?
Yeah. We need to take August off because that's IAU.
Oh, yeah.
But I'll probably
off.
Yeah.
Because otherwise our brains are fried. And my children just run around the house or just glare at me. Where is our father? Okay. And it's so nice here in the summer. Cool. Let me just start getting this uploaded, and then I'll see if I can take like a couple of questions. Didn't see a bunch, so
okay.
And then we'll roll.
I see that a bunch of people are plussing the question on where's Tiny Intern. She's actually working strictly for my center director right now. Her skills at graphics and artwork and layout were quickly identified as something that was greatly needed. And so she was poached, and that's fine because as I've stated, we're running out of money, and every couple of hours that Tiny gets paid, that's 1 hour of Corey's time because he's a senior software developer. And even though he's greatly underpaid for being a senior software developer, he still costs more than Tiny. So she's still around. She's still getting paid to work in the STEM Center at SIUE. She's just getting paid to work on projects for my boss instead of for me.
Okay, here you go. Here's a question from Oleg Striganov. How can a hot Jupiter be tidally locked to its host star when it doesn't have any surface feature for the star to gravitationally hold to?
It won't be.
Yeah.
If it's a sphere, it won't be.
Yeah, it will have a bulge facing towards the star, and that's what it's going to be holding on to.
So the way to think of this is not so much that the same face of the planet is constantly locked towards the star, but the way to think of it is you have a cloud where all of the cloud is getting distorted and pulled towards the star, and that's artificially reshaping the planet, so it's no longer a sphere.
And one question from Nancy, and then we'll wrap it up. Oh, where did it go? Nancy's question.
Now tornado alerts going by. Okay. Be safe, everyone out there.
I don't know where the question went. She had a question about quark. Okay, right. Is the spin associated with the electron the same as the spin associated with quarks? Same kind of thing?
Yes. The spins are fractions of yes, it's the same. It's thirds, but it adds up to a half. So there's wait, that's because that's proton. Proton spin is associated with quarks. Electrons are fundamental particles that are not made up of quarks. Thus, it's okay that quarks have a spin of 1/3.
Sweet. Okay, let's wrap that up. So, hey, thanks everybody for watching. Really appreciate it. One quick reminder, on Friday, we'll have the weekly space hangout. Our special guest is going to be Bast Lansdorp from Mars One, or someone from his team. So that's going to be fun. And then Saturday, the hangout-a-thon begins. What time?
It begins at 8 a.m. Pacific, 11 a.m. Eastern. That is 10 a.m. for me here in the Central Time Zone. Even if you are happily enjoying a life offline this weekend, if you could take a moment in your frolicking in the spring or fall weather, depending on your hemisphere, and donate even $1 and classify even one image on your cell phone, it would be greatly appreciated. So cosmoquest.org/hangoutathon.
Awesome. All right. Well, thanks everyone for watching. Thanks, Pamela. Again, get back to work. I know you got a lot of prep to do, and we'll see you all on Friday and over this weekend. It's going to be great.
Sounds good.
That's it.